All right. So good afternoon, students. The last session we discussed about the different feedback connection types. So there are 4 different ways in which a feedback can be connected. Out of which 2 are using the voltage and 2 will be using the current. Okay, and the feedback can be either series or it could be parallel. Okay, so the first one is voltage series, the second one voltage parallel, the third one current series, and the fourth one current parallel feedback combinations. So we discussed about these things with respect to their block diagrams and also the mathematical expressions in detail in our previous session. That was a chart which represented the summary of the mathematical expressions for the gain parameter feedback and also gain with feedback parameters. Okay, all right. So today we shall just look at the derivations, especially with respect to voltage series and the voltage parallel feedbacks, because they are the most popular ones and the most practical feedback circuits which are being used. So let us just focus on the first one, which is voltage series feedback. There is a bit of substitution, a little bit of mathematics. So you will have to focus on the particular parameters, right? Okay. So voltage series, I'll be drawing the voltage series feedback in short, so that the parameters can be well justified. So Vs is the actual input which is being fed, and let us consider A as the gain of the amplifier, and let V0 be the output voltage. Since it is voltage series feedback, I will not be representing the entire parallel kind of a voltage including the load resistance. I will just be taking it in simple terms. So let beta be the feedback unit, and let us just give the output of the feedback network to the mixer circuit, so that Vi becomes our actual input to the amplifier, and Vi is either the sum of Vs and Vf, where Vf is the feedback voltage. So depending upon the phase of the feedback voltage, the magnitude of input voltage to the amplifier, which is Vi, depends on. Alright, so now let us just look at the things. So what does the statement say? It says if there is no feedback, so if there is no feedback, then obviously Vf will be 0. No feedback, Vf is 0. Then the voltage gain of the amplifier can be expressed as the gain A equal to output voltage by the input source voltage Vs. Now since Vf is 0, we can say Vs is equal to Vi. This is without feedback. Now if we connect a feedback signal in series with the input, so when Vf is connected in series with the input, we can express the input Vi. We are talking about this input, right? So the input Vi can be expressed as Vs minus of Vf. Fine. Now what is V0? V0 can be written as the gain without feedback multiplied by the input signal Vi, where Vi is Vs minus Vf. So if you split the terms and then rearrange it, you will be getting this expression. So what is Vf? Vf is the feedback voltage, which can be given as beta into V0. It is quite natural, right? Vf is equal to beta into V0. So now solving for combining the common terms, you will be getting 1 plus beta A multiplied by V0 equal to A into Vs. Now we are interested in the ratio of V0 upon Vs Okay, so if we want that, that is nothing but it is gain with feedback. Okay, please note the capital A is feedback, it's the gain without feedback. Capital A subscript F is gain with feedback, right? So gain with feedback, the expression is V0 upon Vs, which is A divided by 1 plus beta A. Okay, so that's a very, very important mathematical expression. Okay, so where the term beta into A, it is called as open loop gain. Its significance will be clarified when we talk about oscillators. Okay, so it's called as open loop gain, beta into A. Alright, so what does it state? What is the meaning out of this particular expression? It says that the gain with feedback, okay, is the amplifier gain. Okay, the normal amplifier gain is A reduced by the factor 1 plus beta A. Okay, because 1 plus beta A is in the denominator side. Okay, so what does that happen? This factor affects input as well as output impedance, okay, among the other circuit features. Hope you remember when we were studying about small signal analysis about various configurations, there were 3 parameters which were very, very important. The first one was input impedance, okay, and the second one was output impedance, and the third one was voltage gain. Okay, so these 3 parameters are extremely important. Okay, but now we have got the expression for the gain with feedback. We are yet to obtain the expressions for input impedance and the output impedance with feedback. Okay, so it is ZIF and ZOF, right? Alright, so that was about voltage series feedback. Whenever we say voltage series feedback, you will have to remember the particular block diagrams. Okay, so for that you will have to practice them. Okay, practice a bit. Then coming to voltage shunt feedback, okay, wherein there will be a parallel combination the feedback is parallelly connected with respect to the current source at the input, right? So how is the gain with feedback for the particular network? Okay, very quickly let me just go back to that particular diagram. Voltage shunt feedback, right? So this is the diagram for which we are trying to obtain the expression for gain with feedback, AF. Okay, again, just to remind you, the gain A without feedback is the ratio of output voltage upon input current. Okay, so just focus on the dimension, right? It's not a dimensionless quantity, it is with dimension, and the dimensions are of resistance. Similarly, beta, okay, the dimensions are of conductance, current upon voltage. Okay, so with this, let us just correlate the same diagram to this particular expression. So how do we express it? Gain with feedback is given as V0 upon Is, where V0 is A into capital I small I, okay, subscript, right? Similarly, what is II plus IF? What is IF? IF is the feedback current, which can be expressed as beta into V0. So after substitution and simplification, the expression for the gain is again A upon 1 plus beta I. Okay, because II gets cancelled with II. Okay, here, right? Alright, so we have discussed these 2 expressions. Now your homework is, okay, try to obtain the expressions, okay, for current series and current shunt network. Okay, so you try to obtain the expressions for the gain with feedback, right? All right, so moving forward, let us go through the expressions for input impedance and the output impedance of voltage series feedback. Okay, all right, so how can we express? See, whenever we say the input impedance Zi, okay, it is always ratio of voltage upon current. Okay, so here the input voltage, see, it's input impedance, right? So the voltage which we need is the real input voltage Vs and the input current Ii. Okay, so small I is the subscript. So how can we express? The current I can be expressed as Vi upon Zi. Vi is Vs minus Vf upon Zi. Again, Vf can be expressed as beta into V naught, right? And what about V naught? V naught can be expressed as A into beta, sorry, A into Vi. So altogether, what do we get after two steps of simplification, substitution? We arrive at the expression of ZIF as Zi equal to 1 plus beta A. So it's a very simple 3 to 4 step process. Okay, you can just do it on your own. Okay, simple substitutions. Now the important point is, what is the significance? What can we interpret based on this particular expression? The input impedance with feedback is given as Zi. Zi is the input impedance without feedback multiplied by the product 1 plus beta A. Okay, so what does that state? It states that the input impedance without feedback is multiplied by the factor 1 plus beta A. Now this applies to both voltage series as well as current series configurations. Okay, these figures correlate to the ones which are mentioned in your textbooks. Okay, so how do we represent it in the form of a small signal model? Okay, what has been done here? See, we have the expressions for Zi, we know the expression for AF and ZIF. Okay, and we'll have to find out the expression for output impedance with feedback also. So once we obtain these expressions, we'll have to draw the corresponding small signal equivalent. Okay, and then represent it. So how it is being done, right? You can just observe here. So that's the small signal equivalent of the amplifier and the other block diagram which is being added. Okay, this block diagram gives some additional details. Okay, additional details in the sense the triangular shaped amplifier block is being replaced by the details. Okay, so what do we actually have inside a amplifier? Okay, so you have this input impedance, right, and you have this voltage thing, and you also have the output impedance. Okay, fine. So similarly, voltage shunt feedback. Okay, the same thing, the amplifier is being replaced. Okay, so what are the expressions for the input impedance with feedback? Okay, just observe again, these are substitution based problems. Okay, you can very easily do it on your own, right? So after substitution and simplification, the final expression that you get is Zi upon 1 plus beta A. Okay, so just observe, that's the expression for voltage shunt feedback. Okay, So it means the input impedance with feedback for a voltage shunt feedback gets reduced by 1 plus beta A amount. Okay, and it is being given that this particular expression applies to voltage series connection and also the voltage shunt feedback connection. Then coming to output impedance. Okay, again the output impedance can be given as, after series of the substitutions you will be getting it as ZOF is equal to Z0 1 plus beta A. Okay, then similarly for the current series feedback, okay, it can be done. So just observe how do we represent a current series feedback, especially the amplifier part. Okay, so here the output impedance is in parallel with respect to the current source. Okay, so that's the difference in the case of a current series. Okay, and finally the expression for output impedance for a current series feedback is Z0 multiplied by 1 plus beta A. Okay. So when we try to summarize everything, okay, what do we see here? For a voltage series and for a current series, the input impedance with feedback gets increased. Okay, so please observe the input impedance with feedback increases for voltage series and the current series. Okay, so can somebody just let me know whether feedback improvises the overall voltage series and the current series connections? Does it improvise, does it help, or does it degrade if the input impedance increases? Let us just focus on MOSFET, okay, or a JFET itself in that case. Okay, we usually say that VGS, okay, we apply some VGS, and what about IG? IG is 0, right? Okay, the gate current is 0. So that means, what is the impedance here? Okay, ideally it should be infinite, and practically it is in mega ohms. So when I am using, it could be a JFET or it could be a MOSFET. Not an issue. If it's a MOSFET, then the input impedance is still higher. Okay, it is much better. Now using such devices and constructing amplifiers with them and using such amplifiers and then taking a feedback, and then providing it back to the amplifier, and then taking more than one stage, we are trying to improvise the input impedance, increase. Okay, so when this happens, it is quite natural that the gain of this particular circuit will reduce a little bit. However, the stability, which is a much more important parameter, increases. Okay, now you may ask, sir, how come the stability increases? See, higher the input impedance, okay, much better control will be at the gate side, especially within the amplifier. That naturally improvises the stability of the overall network. See, these are all linked in parameters. Okay, we talk about a JFET or a MOSFET, which is the core device, and an amplifier consists of a JFET, and amplifier plus a feedback, okay, will be the complete block diagram. Okay, so the point is ZIF increases in voltage series and current series. But what about voltage shunt and current shunt parameters, the configurations? Here the input impedance decreases. Okay, in both the cases. What about the output impedance? For a voltage series and the current series, the output impedance decreases. Sorry, only for the voltage series, but for the current series it increases. Similarly, output impedance with feedback for a voltage shunt configuration decreases. For a current shunt it increases. Okay. So while designing an amplifier, first of all, designing an amplifier is not a simple thing. Okay, it's a very complex thing, because you will have to consider so many parameters, right? You will have to consider the gain, you will have to consider the stability, you will have to consider the input impedance, the output impedance, whether the impedances are required to be high or do they need to be reduced. So all these factors matter a lot, right? Okay, so the task for you is, okay, you will have to derive the below parameters, okay, on your own. Okay, so you can start with the voltage series. In fact, the voltage series is the most important one. Okay, so at least try it out for voltage series and the current series. Okay, the ones which I have just discussed. So you will have to do it for input impedance, output impedance, and the gain with feedback. Okay, and then we have a problem. Okay, a numerical problem, which is, I hope it is based on voltage series. Yes, it is based on voltage series feedback. So you have been asked to determine the voltage gain, input, output impedance. Okay, so the voltage gain with feedback is AF, the input is ZIF, the output is ZOF with feedback. Okay, wherein the normal gain without feedback is -100, the input resistance is 10 kilo ohms, output resistance is 20 kilo ohms. Okay, and you will have to do it considering two types of feedback parameters. Okay, the first case it is -0.1 and the second case it is -0.5. Okay, so again it's purely a substitution based problem, provided you remember these equations. Okay, so you can do it at your home. Okay, so try to solve it. I just wanted to tell you that the more you practice these kinds of things, you will remember them. Okay, unless you practice you cannot remember. Okay, all right. So the next topic will be on oscillators, which we will start on Monday. Okay, meanwhile I am yet to send some numerical problems to you, so it will be forwarded to you through WhatsApp. Okay, all right. So any doubts, students? Yes, if there are any doubts then you can ask.